Hello there, great person, and welcome back to this new science reaction. Today we're gonna react to a video called How Does Hawking Radiation Really Work? So I'm quite curious to that because I think I probably only have the simple explanation there. So I will probably learn something as well today. So for you who are new here, I'm a quantum physicist. Um, and yeah, I'm watching these videos just to give you my thoughts on it. I'm not the expert in all of this. There are some things I know more about, some I know less about. So yeah. So beware, I will pause the video probably quite often because I want to comment immediately because otherwise my thoughts will just go away and I forget them because I forget things often. So let's just get into the video. It's from the Science Asylum, and I actually absolutely love their content. Have seen other stuff of theirs, and let's just get into it and let's see how Hawking radiation really works. I'm curious. Let's find out.
To the Great Courses Plus for helping support this episode. Hey crazies, I've been skeptical of Hawking radiation for a very long time. If nothing can escape a black hole, how could a black hole possibly radiate anything?
Yeah, and the great depiction of a black hole there, a really good one.
It's ridiculous. But after reading the scientific papers on the subject, I'm kind of on board with it now. Hawking
That's
radiation
good.
has a lot more in common with strings than particles. Let's get into this.
Yeah, that is actually, and it doesn't even have to be string theory, although he might refer to that later on. What is quite fascinating to me is that very many things can be described by spherical harmonics or, oscillations of a bubble or a sphere. And that's quite powerful. And I think there are even things of the black hole you can describe with that. So I really like that. It's so interesting. So let's see what they do here and what you saw the standing wave theory he had. Yeah, standing waves, they are powerful. You should know about those. So if you are interested in physics, that's something you really should read up on. Standing waves. It's quite simple, and I think you even do it in middle school or I don't know, high school, or I don't know, some our school system in Germany is named a bit differently, but the schools. But yeah, you should read up on that. It's very interesting, and you can do so much with it, unbelievably much.
If you've heard of Hawking radiation before, then you've probably heard the following explanation. Particle-antiparticle pairs are popping in and out of existence everywhere all the time.
Yeah, that's
If one of these pairs forms on the event horizon of a black hole, one partner inside and one outside, then one can escape and the other can't. Without being able to recombine, they can't annihilate, which means they've popped into existence but can't pop back out. The particle outside the event horizon needs a lot of energy to escape. That energy must come from somewhere, and the only thing around is the black hole. If the black hole loses energy, then it loses mass, which means it shrinks, until eventually it's gone. Except this explanation leads to a lot of questions.
Yeah, okay, let me try these because I really, I would have explained it a bit differently because it's about the mass of the particles that are created. Yeah, the problem is quite obviously. So why would it fly out of the black hole? Why not into it as well? I mean, because you have a conservation of momentum. So if one goes in, one has to go out. That's okay. But it has to be okay. It has to be the speed of light. So it will escape the moment. Let's say you don't have a rotating black hole, so it would probably escape the moment it has a momentum that is not directly towards the event horizon, and therefore has to be the so one, let's take, I don't know, let's take this remote. Let's take, this is the event horizon, so one of the particles has to have a momentum and the other has a momentum in the exact opposite direction because they have to sum up to zero because you can't create momentum as well as energy. So has to have exactly the same. So one of them, yeah, I'm doing, okay, let's do it with this. It's like this. This is the momentum on both sides of both particles, and it's like they are one thing that is in the opposite directions, So one always falls in, one I mean, if I do it this way, it's the same thing. One will point into the event horizon, one outside. So we are having photons that are created, not matter particles. So the photons have the speed of light. So if they are outside the event horizon, they will go out, obviously. So yeah, but my argument would not be with the energy, but more with the mass. Okay, it's the same, in a way. But I think the mass argument is better because you, so to speak, the quantum fluctuations create mass, and because you can't create mass, the mass is taken from the black hole. But it's probably wrong too. It's not something I've read up a lot on. So, and what he said is, in that argument, I also don't see how it has to be the energy of mass and not the rotational energy, because as we know, we've seen the other video where I reacted to that black holes spin. Most of them do, and so why not that? So black holes can have at least 3 types of energies. So they can have mass energy, so potential energy, so to speak. Then they can have angular energy, so rotational energy, not rotational energy, and they can have electric charge energy. But I'm not so sure about the charge thing. Never read up about that. So if anyone knows, I mean, there are some clever people here in the comments, so you can tell me as well. So yeah, that's why not take it from the other forms of energy. I could find arguments against it, but let's just watch the video because he's gonna explain it. Because I know he is very good at explaining things, and he's got a very deep understanding. Or him and his team, they are very good.
Shouldn't the infalling particle add to the mass of the black hole? But then the pair of particles came from nothing, so is energy not conserved for black holes? Why does the outside particle even have enough energy to escape?
Okay, so those two I kind of covered. So the particle falling into the black hole has, so what would it have? Double the mass of the pair, minus double the mass of the pair, because the pair gets created and one goes out, and that energy has to be taken away, but also the energy from the particle falling in, I think. And what was this other point? Yeah, why does it take the energy? That's what I said with the, I think, with the electric charge.
These are the questions that always came to my mind. It's why I always thought
But
Hawking
going out,
radiation
it's
was bogus.
photons.
In fact, I had every intention of this video being a debunking extravaganza. But then I read several scientific papers while researching, including Hawking's original work, the title of which is solid YouTube clickbait.
It is,
As it
though.
turns out, black holes do radiate away their mass. It's just that
I'm sorry, it has nothing to do with this, but I sometimes try to do. I nowadays try to do it. I did not do it when I did my PhD thesis, giving papers these cool intros, like what did we have? I don't know. And then everything broke down. How students perceive experiments, and I don't know. You always have these catchphrasy titles, and it works even in papers. It's so funny. It's like it works on YouTube. Like a colleague of mine does that a lot. He is very good at it, and another colleague of mine, she's also exceptionally good at it. It's so funny, and these paper titles, they can be so funny. Hawking, yeah, great job, mate.
particles popping in and out of existence is a bad explanation.
Because they're not
This
dots.
is not how Hawking radiation works. Good old Hawking made up an incorrect explanation because he thought it was easier for the general public to swallow. But the
Oh, yeah. Wow, okay. Yeah, that's something. It's like with the Higgs field. I actually was in a conference once where I think there were several people from CERN. I was invited with my, back then I was still doing my PhD studies, and my supervisor was invited, and yeah, some CERN physicists. And we tried to find an explanation, or more, the CERN scientists, they gave their explanations. How could you teach the Higgs mechanism? And that was quite hard, because they always had this one. No matter what picture or image or story they came up with, it was always obviously wrong because it wasn't as precise as the formula or whatever, obviously. But yeah, that was so interesting, and this seems to be the same thing. So I know I don't know how good Stephen Hawking was in explaining things to laymen, and I would consider myself a layman in Hawking radiation, more or less. So yeah, this is one of these explanations you can give, and it will go so far, and then you start understanding that there are many holes in the explanation. You start hammering on them, and you start to try to understand what's really going on, and that's how you learn about this. That's how you should learn about this, because then you understand, okay, there are no little particles, there are no balls flying around a black hole. It's you know, it's so great, but that's a question: how much can you simplify things? Because you always have that one guy in the audience. If you suggest something like this, there's always this one guy that says, no, then it's wrong. And yeah, depends on your definition of wrong, but yeah, if I go with your definition, you're probably right, mate. So you know what I mean? It's I have something against right and wrong even in physics, but because it's more complicated than that. And yeah, that's something we as physics education researchers also deal a lot with these problems, like how simplified can you explain something? It's actually quite hard in many cases. And the Higgs thing, that was a great cartoon one guy had. I think he's still working at CERN, and yeah, hopefully I will meet him if this stupid pandemic is over. But yeah.
Real explanation makes a lot more sense and doesn't raise so many questions. As long as you understand two things.
Oh, let's see.
Black holes and quantum fields.
Oh yeah, so no problem. You just need to understand everything.
Quickie review time.
Yeah.
A black hole is what you get when you cram a lot of mass into a very small space. They're so black that we can only see them when they have material
That is a
falling in,
great
or when light
animation.
stars are orbiting them. Getting that much mass into such a small space is
Very
not
good.
easy, which
Very
is
good.
why these tend to only form at the end of a large star's life. The outer edges of the star get blasted away by the supernova, but the core collapses in on itself. If there's enough mass in that core, it'll collapse to form a black hole.
Yeah.
You mean it'll collapse into a black hole, right? No, I mean what I said. It'll collapse to form one. The collapsing core material is not the black hole. The event horizon that forms around it is. Black holes aren't material things. They're space-time itself. The event horizon isn't a solid surface.
Yeah, okay, I see. That's interesting as well. Wow, this is a very good video. I love him. I've seen things of his before, 4 or 5 videos. I loved him. He's such a great guy. He explains things correctly and very, very nicely. So this one, yeah. So what he's saying is that this is not the black hole is here. Or what? No, I think he even says, yeah, the event horizon belongs to it, because it's the distortion in space-time. So technically it would also be everything where you here see the things getting distorted, probably. That's very good, yeah. So that's also a question. Is the black hole just the dot? Is it the event horizon? I mean, technically it has to be the event horizon, because that's in the metric. So if you use the Schwarzschild metric, you get this singularity and this one is a real singularity. This one you can transform away, I think. I've never done it. I would love to see someone do it one day, just because I'm interested in it. So, but yeah, so technically this is the black hole, and then yeah, you have the gravitational, the space-time distortion that it goes to till infinity, like with the electron wave function. It's not really infinity, but yeah. I think it would be reasonable to say it's until you don't get this gravity lensing effect anymore that you can really detect. So, but that's also, yeah.
It's just a place we can't see.
Great video.
It's
Very
a
good.
collection of points in space and moments in time that have been separated from the rest of the universe. Once an event horizon forms, it doesn't matter what happens to anything inside it. Black holes are like spherical blemishes in space-time.
Yeah.
Black balls in space! They'll bend the paths of anything inside that space-time, including light. An accretion disk is what happens to material as it falls into a black hole. This is what it would look like if you try to see it from different angles.
Yeah.
If it can do that to
Wow.
light,
That is such a good. That's what I I think I tried 3 times to explain that in other videos, so you can see top and below. It's such a great video. See, he's got great stuff. Great stuff here. Something I wanted to say. Yeah, by the way, I don't know if you know this, but I think before actual black holes with their properties were known, there were dark stars that they theorized. And so that was just a star, really a solid mass that is just so small that light couldn't escape it, but it was still a body. It didn't collapse in their formula because they didn't know about it. And I don't even think they had Einstein, but I would have to read it up. Such a great animation. Very good. Let's see what our quantum fields.
Okay, this one is tough, and it's definitely something I learned more recently. When I feel motivated, I read through a little more of this textbook. I've learned enough so far that I think I can explain what we need to know for this video. Here's
I have to read up more on that as well.
We like to imagine that particles are little bits of matter flying around through space.
They're not.
But in quantum field theory, there's just a field filling space with quantum properties.
Yeah.
Each point has a little uncertainty, but they all hover around 0 for the most part.
And see, this is what I mean. It's like this blinking is the measuring process. So you have this cube, and somewhere around there it's random where you measure it, but if you measure it very many times, it's like a trail in a fog chamber, you know? And that's what they do, and that's why it sometimes jumps a bit, because it's not a path. It's just, you know, this... I'm so amazed by this. This is such a good video. Wow. I can already recommend it. We are not even halfway through.
A particle is just what it looks like when one of those points isn't hovering around 0. There's a little concentration of energy there. As that energy moves around, it looks like a particle is moving around.
I wouldn't even say it's energy, though he might be right. I think it's more like charge or anything that interacts. So I would do it more generally. Also, you could argue that energy is the same, but yeah, I think it's more like an interaction.
That isn't the whole story, though.
Yeah.
It understates the weirdness that is a quantum field.
It does.
This field is filling space with quantum properties. But what makes those properties quantum is that they're probabilistic. Every point in space is teeming with everything that could possibly happen there. We only see a particle somewhere when we reduce those possibilities to 1. The thing is, though, it's possible for those non-particle points to become particles.
Yeah.
Considering all the possibilities at once in such an abstract way can be a bit overwhelming. Unless you're an observer from Fringe. So
good. I love Fringe. Such a great show. So glad that it's get to end it. Wow, this is, yeah. It's like, yeah, all the states are meshed together to superpositions, and the superpositions can even be expressed in other states. So yeah, it's so good. So good. I love quantum physics.
We try to lean on visuals that we
Great
already
stuff.
know. Maybe you can try imagining all this empty space isn't empty, but is filled with particles. Virtual particles. That's where that popping in and out of existence idea came from. It's complete nonsense, though. We call them virtual because they're not real. But nonsense
So why not call them imaginary? I'm sorry.
is okay, if it's helpful. For Hawking radiation, virtual particles are the opposite of helpful. Too many questions. We need better nonsense.
Yeah,
Believe it or
better
not, Hawking
nonsense.
radiation has a lot more in common with strings than particles. Consider a string stretched between 2 heavy blocks. If you pluck the string, it'll vibrate. But some vibrational frequencies are easier for the string than others.
Yeah, so that's it. And it might be because in Germany we have 2 words for this. There is string, like, I will just say the German words. So we would have Band, and we would have Saite. So a guitar string is a Saite. So it's a completely different word. So that's why I get confused with the string word here, because I always associate string theory, I think, because many videos cover it. So yeah, but the guitar string, yeah, that's the one you need to understand.
They're the string's
Because it's
natural
quantized.
frequencies, also known as
Quantized.
normal modes.
Yeah.
These are the ones where the wave loops fit nicely on the string. There are an infinite number of them, but the first several examples are the most dominant. 1 loop, 2 loops, 3 loops, and so on.
Yeah. And by the way, that's exactly how an atom is. Electrons within an atom are the same. This one is like the ground state, first excited state, and so on and so on. So to speak, if an electron goes from this to this, it like I would with students we always do it like they give away 2 nodal points, and nodal points are the points where it doesn't move. So there is a nodal point here, and there are 2 nodal points. Here is one and here, so it loses both of them because there is none. So that's the quantization of the string that, or of the electron that gets out as radiation, whatever. That's how we explain it. And I really love the string. I never really understood, not understood it, but had it on my radar, so to speak, when I studied. But my supervisor, he's such a great mind. He really does a lot of things, explains a lot of things just with this, just with what he's showing here. You can explain black holes, you can explain orbitals, everything. That's so great. It's such an interesting thing.
Ooh,
Spin,
yeah,
you can explain
real
spin.
nice. Anyway, they're all available to the string, unless we pinch it. If you pinch the center of the string, that point must remain stationary.
So
which
you
eliminates some
lose
of the
half of
available
them, yeah.
frequencies.
Yeah.
You pinching the string changes what the string can do. Black holes do something similar for quantum fields. Now, rather than having a flickering box represent the point in space, we'll just take snapshots of it across time. This pattern can be expressed by a combination of positive and negative wave modes. The positive modes go forward in time, and the negative modes go backward in time. Hopefully you can see now why a quantum field is kind of like a wave on a string. Usually, nothing weird happens. The positive and negative modes tend to cancel out. When someone says virtual particles, this is actually what they're talking about. The quantum
Yeah, because and that's also because a virtual particle. I just can explain it to you topologically. So if you have a strip of paper wrapped around, you can just distort it. Like you can. I don't have. Oh yeah, let's take this broken bow tie. So if you have this, I don't know if you can see this. You can like if you do a virtual particle, you can just do this, and you have a virtual particle, but it's still the same, you know. But it's a distortion. So what a black hole theoretically does is do this, and then pull out the 2 particles, which is I have to think more about that. But that is very cool. Good explanation he's got here.
quantum wave
So I didn't know that I already understood it. Very good.
activity of the vacuum.
Very good.
For contrast, a real particle looks like this,
Yeah.
and a real antiparticle looks like this. What does this have to do with Hawking radiation? It's all about that vacuum activity. Like I said, these vacuum modes usually cancel out, but not when there's a black hole. The formation of a black hole kind of pinches the quantum field, like your fingers did with the string. Remember how pinching the string made some of the vibrational modes unavailable? Well, the black hole does the same thing with the waves in the quantum field. Some of the modes before the black hole's formation aren't available after. By making part of the quantum field unavailable, the modes don't cancel anymore. The black hole has turned the vacuum into a particle-filled region of space. The key word there being region. These new particles are not localized to the event horizon. They're
And they never are, because the particle doesn't exist in a point-like thing, because it's always a wave, as he says here, because he's clever.
emerging from a large region of space around the black hole. A region that's a few times larger than the event horizon. And let me tell you, it's a lot easier for particles to escape from way out here than it is for them to escape from in here. They're going pretty fast though, right? Oh yeah, definitely. Fast. Hawking radiation is almost exclusively photons.
Yeah, speed of light.
Photons. What's a photon? Hawking radiation is almost exclusively photons, otherwise known as light. And that light has a gigantic wavelength. It's upwards around 80 times the radius of the black hole by the time it finally escapes. That's not visible light. That's extreme radio waves. I'm serious when I say it isn't localized. These new particles can't just come from nowhere, though. All particles have energy, and that energy has to come from somewhere. Conservation of energy shall not be violated! And the only thing around is that black hole. Remember that a black hole is not a physical object. It's pure, unadulterated space-time curvature. The energy for Hawking radiation comes from that curvature, which means the curvature will decrease. And according to Einstein's equation, less curvature means less mass. A radiating black hole will lose mass and shrink. But unless there are some micro black holes roaming around, not a single black hole in the universe has begun shrinking yet. They're emitting Hawking radiation so slowly that what they're eating still makes them grow. Even the isolated ones are eating the cosmic microwave background fast enough to grow.
Yeah.
Huh, it's no wonder we haven't detected it yet. In the unimaginable far future, the universe will cool off enough to allow black holes to shrink. It'll start slowly, but speed up as it shrinks. The energy of the radiation will grow until eventually it's visible. In the black hole's final moments, it'll erupt violently, with massive particles, not just photons. Black hole explosions indeed, Mr. Hawking.
Boom.
When this eruption happens depends on the black hole's size once it starts to shrink. For stellar mass black holes, it'll take an octodecillion times the current age of the universe. That's 10 to the 67 years. For supermassive black holes, it could easily take 1,000,000 Google years. The bigger it is, the slower it evaporates. No matter what though, all black holes will evaporate, eventually. But not because particles are popping in and out of existence at their event horizons. Just like pinching a string makes vibrational modes unavailable, a black hole kind of pinches space-time, which makes quantum modes unavailable. Doing so, the quantum vacuum doesn't cancel itself anymore, and you get particles. Those particles, which are almost certainly photons, are called Hawking radiation. And that radiation carries energy away from the black hole. Eventually, so much energy will get carried away that the black hole completely disappears. A black hole might be a blemish in space-time, but it has a mechanism to correct itself. Which is kind of beautiful, actually.
It is.
So, did this help you understand Hawking radiation a little better?
Yeah, it did. What does he have? Nothing more. Okay, so subscribe to him. He's great. Yeah, so that was my reaction to this. Went on for longer than I thought, but what can you do? So I really like this video. This was a very, very good video. It was more like I was just happy that he explained it so well, which yeah, I did not. Did I have criticisms? Well, in the end, he still showed particles, but I mean, yeah, we've seen the correct thing. But I mean, why not use it in the end? But I mean, who cares? Great video. Yeah, that's a better explanation. This makes more sense, actually. So if I would have had to explain it topologically, I would have explained it like that as well. But no one does that. So yeah, like that's the important thing. Again, we see it again. There are no dots swirling around. It makes no sense anymore. You can't explain anything. So yeah. Anyway, if you like this, consider liking and subscribing. I will do a Halloween live stream. I will try to set it up. Perhaps I won't be able to, but we'll play some scary videos. Perhaps do other stuff. Play a scary game. And perhaps watch science videos. If you have suggestions, we might do a live reaction there. Would love that as well. So anyway, if you like this content, consider liking, subscribing, and I hope that you have a great, great day. And see you soon. Bye.